here. Thank you so much. Good morning, everyone. All right. So let's jump into it. Just one thing, guys. Make sure you do switch on your webcam during the week, especially to make sure it works for Friday, because you will probably receive 0 if you do not have your webcam on while writing your tests. So yeah, I'm sure I don't need to talk about it. It's already halfway through the year. So, but yeah, just wanted to mention that. Okay, now let's get into it. I'm just going to share my screen, and then you guys just give me a shout if you see it. Let me just share the correct window. Right, give me a shout if you can see anything. Thank you, Kenneth. So you should see my screen now. I actually wanted to open Excel as well. Let me see. Let's go to this one. Yeah, just make sure you check. It's probably someone else there, but okay, just make sure you can see my screen. Apologies for yesterday. I see we were kicked out. They are checking into what happened to make sure that it doesn't happen again. So I remember Ruan sent me a message. If Ruan is on, is Ruan online? Ruan Leanders. But if you send me a message, just send it again privately later, and then when I get a chance, there's Ruan. Then when I get a chance, I'll just have a look at what the question was. Right. Okay, so we're going back to this slide, number 2, the mixed versus pure IP slides. I just want to go through the explanation there a bit, although we're going to go through it again, but just a bit more, because I'm sure some of you are probably asleep by yesterday afternoon. So let's see how. All right. It seems to be stuck on your side. Let me just quickly reshare the screen. So just give me a moment. It seemed to have. Let me say the entire screen so that we avoid any going, closing, and opening and whatnot. PowerPoint. You guys still good? You ready? Oh, maybe not ready, but are you good? Can you see everything? You hear me? A little bit slow. Yes, or 5. Depends on how long it takes. Okay, not, yes, no, yes. Maybe I should read the scenario and then you could tell me. All right. write something. Or is it still lagging? Just to see if it's really that bad or not. Let's see. Let's say, for example, a table requires 1 hour of labor. Same still. Okay. On it. Let's have a look how it goes. And then if it's really bad, then you can let me know, but it should be okay enough. I see that signal is all good and so it should be okay enough. Let me just share my screen. Let's see if it's still better. I'm just going to share then the window and not the entire. Okay, maybe. Seems good so far. Okay, now I've got the presentation open. I'm going to start talking, then you let me know how it is, but only if it's really bad, right? Otherwise, we go on. All right, let's see. Okay, so the LP on its own is the same as usual. So you're still setting up your constraints and your objective function. We're not at binary problems yet. This is just a normal LP with the number of items, and then we work with that. So let's have a look. If we check there that they manufacture table and chairs, we assume those are the items that we want to work with. They talk about profit, so I'm assuming we're going to maximize that. So even if they don't specify if you have any profit or revenue, you would like to maximize that. If you only have costs, then you're going to minimize that. If it's in terms of time required for employees to do something, you want to minimize that because that will obviously be better for the business. So I'm just saying it doesn't necessarily have to specify max this or min this. Okay, so we've got profit that they give us. If they were cost, we then subtract it from the profit, but the main idea is then to maximize profit. Okay, so that's the usual max. Okay, what will give us profit? We know a table can give us profit and a chair can give us profit. So we're going to then make table our x1 and chair our x2. And then we go and say, okay, what is x1? Okay, x1 is the number of chairs so that we can figure out how many, number of tables, so that we can figure out how many tables and then times it with that 8 rand to say, okay, what's the profit then? And then x2 is the number of chairs, and then we can multiply it by the 5 to check how much profit. Okay, so I'm not going to write all of that out. It's on the slides. But once we get there, we just want to quickly set up the objective. So max z equals to the profits. So for x1, the profit is 8, and for x2, the profit is 5. And if you add them up, you get the total profit. I don't see any cost involved. Then we've got constraints. So let's see if you guys can pick up. What are the constraints about? Like, what are our limitations or demands? What are they about? Just to make sure you guys are still with me. Yes. Labor and meters of wood. That's perfect. Right, so if you check further in the statement there, they say currently 6 hours of labor and 45 square board meters are available. So we have limitations or demands. So we can now go and say, okay, one of them is going to be 45 and one of them is going to be a 6. The 6 is specifically for labor. Sorry for writing that cube. The 6 is going to be for labor, and the 45 is going to be for your wood, square board meters. So when you get the values for your x's, make sure that it's in the same measurement as that specific constraint, obviously, not everything. So if I say labor 6 hours, and then they say for a table it's 1 hour, I'm happy because it's all in hours. So Manisha, yes, it's going to be 1 for x1 there. And then the amount of hours for labor for x2, which is a chair, is also going to be 1. So the total of hours plus. And then now my question is the sign. What sign are we going to use? We're going to use, you guys are too quick. I wanted to give you options, and now you guys give me the answer. That's much better. All right, so 6 there. Just want to make it look a little bit better there. Otherwise, it looks quite horrible. Neighbor. Yes, less than or equals to. If you only have that amount available, you can only use less, but equals to is 100% necessary because 6 hours is available. So if you want to use all 6, great stuff. So less than or equals to. Okay, and then like Henry also said, it's actually for both the same. So I'm also going to use less than or equals to there for the word. Then we go further on, we say, okay, now with all of that, how many board meters of wood? So just checking, is the 45 also meters? Yes. If I check for a table, it's 9 square board meters. Yes, so I'm happy. I use 9. What's the next value? The x2 coefficient. What is that? Perfect. 5. Perfect. Okay, so we set up our, for now, LP. So we would usually then go and specify x1 or x2 should be greater than or equals to 0 because we want to make a positive amount of these items in order to get profit. All right. Now we go to the next step to say, okay, now to make it an integer programming model, we are basically saying that we don't want to make half a table or a quarter of a chair. We want full items. So in that case, you would then say, which of these items do you want to have integers for? So if it's a pure IP, like I explained yesterday as well, pure integer programming model, then you're saying both of them must be integers. So then you're going to go and say x1 as well as x2 must be int or integers. If it's mixed, then maybe your scenario doesn't require all of them to be integers. Maybe someone could tell me, but okay, you can make half a table and then sell it as still a table, but just a smaller table. And then I'm going to be like, oh, okay, then maybe x2 should be the only one that's int. Then that's a mixed IP. Then you only specify the one that actually should be an integer, and you focus on that one only, making that one an integer. Right, but we're going to stick to right now pure IP. Okay, so we're going to stick to saying, okay, it should be greater than equals to 0, but they should also be both integers. Both integers as well as greater than equals to 0, because I don't want negative integers. All right, now we're ready. Okay, so let's see. So I just explained the pure IP there. Graphically, when you have a pure IP, Christy, when you have a pure IP, you are basically saying all your variables must be integers. Doesn't matter how many you have, x1, x2, x3, x4, doesn't matter. You're then saying all of them must be integers. Okay, so we're going to stick to this one being pure IP. Just to see it graphically, if you got your optimal solution here, the values were not actually integers. So now you're saying, no, it must be a pure IP. So I'm saying the only options then are values in the feasible area where both x1 and x2 are integers. So for example, this dot that I'm coloring in, x1 there is positive 3 and x2 is a positive 3. Both are integers, so that's a candidate or a possibility. Right, it might not be the best, but it's a possibility as soon as I have both of them as integers. If I only want one of them to be an integer, so let's say it was a mixed problem, just want to go to this one. I'll come back to this. Let's say, for example, didn't we have the other one around? There we go. Let's say, for example, only chairs should be integers because tables we can make a half of, so we don't really worry about x1 being something like 2.5. We don't worry, that's okay. But x2 has to be an integer. All right, so if that happens, then we have less options to work with. So if I take that optimal solution we have right now, and I check what options we have, we're only looking at x2 being an integer. So x2 can only be in the feasible area 1, 2, 3, 4, 5, and 6. x1 can be anything. So let's say I take this. So check where my dot is colored in. x2 is an integer. x2 is equals to 1. But x1 can be anything. It can even be a half there because we said it's okay if it's a mixed problem. So meaning not all of them are integers. Right, so x1 can be anything. It can be there, it can be there. As long as you can see my line there, as long as x2 falls on that integer. If it was the other way around, then your lines will then not be horizontal, but vertical, because then you're focusing on making x1 integers. Right, so just to show you visually what I'm talking about in terms of making them integers, you won't necessarily have to focus on drawing that, but it does help to understand the concept. Right, now let's go back here. Anika, yes, they can definitely specify which could be, but in some scenarios, it's quite logical for you to be able to identify what should be not. We're not there yet. We'll still learn about the different IPs, but for this example, they would have had to specify, because I mean, you can argue it kind of saying, but you can use resources. And then, but okay, on assessment queue, if I give you blocks to fill in to do branch and bound simplex, for example, where you have to make something integers, you're going to be like, oh, okay, so I have to. But yeah, it depends on the IP itself. But yeah. Okay. Now, just to show you something very quickly, because most of us would normally do rounding by, oh, let's go round it normally like we normally do. So I just want to show you that it's not always the best. So we're going to quickly go back to the pure IP. So we get our optimal solution. We see, oh, okay. First off, I told you yesterday, you need an optimal solution to start with, to first see that there's a problem or not. Okay. So you see now both of them are decimals. Okay. We said it's a pure IP, so we're going to assume we want both of them to actually be integers. Okay, so now we go, so okay, let's just round, right? So let's round both of them down. Guys, this is not what we're going to do. I'm just showing you that this is not the best idea. Okay, so this is not what we're going to do. Right, so let's round down just to see what's going to happen. So if I round x1 down, I'm rounding it to a value of 3. If I round x2 down, I round it to a value of 2. If I substitute that into my objective function, which was this 9x1 plus 5x2, z equals that. If I substitute that in, we're going to get a z of 34. Now, the value itself, or the position itself, is perfectly fine. They're both integers. It's in the feasible area. But is it the most optimal? Meaning, is it the best? Is it the best? Did I make a mistake there? 10, 9, 18, 27, 10 plus 27. Oh, yeah, you're correct. No, wait. Right? You're making me... Is it? 9 times 3 plus 10. Yeah, it's 37. Sorry, I'll fix that. But that's then 37. Just check the slide. I don't know why. I'll have to fix that. So please make a note of that. Please, please, please. But 37. Right. But yes, Christy, not necessarily the best. Okay. So we round it down. We got a z of 37, but it might not necessarily be the best. Okay, now we say, but let's try something else. Let's try rounding up. Okay, if we round up, instead of these values, yeah, now you're making me doubt myself. Aye, thank you, Vian. It's an 8. Thank you, Vian. Now that value makes sense. Now we can say the slides was not incorrect, right? Just want to get my pin back. Thank you, Vian. So yeah, 8x1. So if we substitute that in with the 3 and the 2, just to go back there, is going to be 34. Okay, but still, that's not the point. It's still saying it's not necessarily the best. All right. So you can probably guess that it's rounding is not going to work, but let's see. Now we round up, we make it a 4 and a 3. Now, guys, if we make a 4 and a 3, will it even be feasible at all? Quickly check. If we make x1 4 and x2 a 3, will it be feasible at all? No. So if we have x1 at 4 and x2 at 3, it is definitely not feasible. So that's not even a possibility. Okay, so no, that's not going to work. If you round down and up, we can try the normal methods that we normally do. And just remember the 34 and the infeasible so far. If we take x1 and we say, oh, it's above 0.5, so we go and say this one goes to 4, and x2 goes down, goes to 2. Let's try that one. So x1 equals 4, x2 equals 2. Quickly tell me what the z value will be for that. Remember, it's 8 x1, not 9, plus 5 x2. That was 42. Okay. Are you sure? Right. 8 times 4 plus, yeah. Armando, you made me think they like, wait, what? Okay, so x1 is 4 and that one is 2. But the problem with that one is, okay, let me not tell you. What's the problem with that one with 4 and 2? Even though you can see it on the screen, but shh. What's the problem with x1 being 4 and x2 being 2? Even though it's a nice z value of 42. So you guys are typing. It is a max problem, so you want the highest. But so that's not the issue. And it is lower than 45, but we want integers, so that's not an issue. Justin, yes. Henry, yes. You guys, yes. Very good. It's just literally just outside of the feasible area. So close, but not there. Okay, so that one's also infeasible, not an option. Okay, so the only feasible one with our rounding was this one. Now we go and we say, but is it though? Now randomly we do solver just to check. And because obviously solver does everything in the back, you'll see the z value 40. Is 40 better than that 34 we claimed was our rounding option? Yes, remember it's a max problem, so you want a higher value. So that rounding did not give us the best possible solution. The best one would be where x1 is 5 and x2 is 0. So if we go check x1, 5, and x2 is 0, we were quite far from it. Really far from it. I hope you can see it. Right, so just doing rounding like you would normally do is not a very good idea. I hope you see that and you realize that we need different algorithms to explore different paths and make sure we get to the best one. Right. So, yes, I'm Andre. We're now going to learn what algorithms we're going to use for this course. There are more, but we're going to focus right now on what we call the branch and bound simplex algorithm. Simplex hinting towards we do it the same as we normally do with dual and primal, a lot of similarities there. And then we've got cutting plane, simplex algorithm. It also has some similarities there. We just have a different constraint. Just give me 1 minute. Just want to close my door. Okay, so hint, remember solver, because we might need it to check. All right, so we're going to go through branch and bound simplex first. That's our biggest one. And then, but just to show you on the mixed it works, even if you do rounding, it's not going to work well. But even if you do rounding, then you're only focusing on rounding the one value. But we want to then just make sure we make that one value that we specified or that we want to make an integer. We focus on that one and we don't care about the other one as long as it gives us optimal value. All right, so let's get started. So we're now going to go to branch and bound simplex. So branch and bound simplex is our first algorithm we're going to use. So it's quite long, but it's because it's actually created to try and find all the possible solutions. And then at the end, you can decide which one is the best. It's just to basically go through all the points there in the graph that we want to focus on and give us the best solution so that we don't miss anything. Because Armando, you also said now, like, how do we get to that 5 and 0? We have to then search for it in essence, basically. Okay. So I'm going to start teaching you now the branch and bound simplex algorithm. So your first algorithm for the course. Right. There we go. We're going to focus first on pure, and then I'll explain the concept of mixed, because then you'll be able to do it on your own, because then you only focus on the one. Or more than one if you have more than 2 variables. It's not limited to just 2 variables, guys. Already in LPR, you can have as many variables as you need. It's just depending on how you set up what we call now an IP, you specify which one should be integers, and that's what you focus on. Okay, so we're going to focus on making both of them integers. So here's all the steps on getting that nice IP of ours that we that I already did with you. Where for some reason I used that constraint, but anyway, they were specifying both of them we want to make integers. All right, so now graphically what we're going to do with branch and bound simplex is we're going to subdivide the problems. So pure IP, first of all, just to show you in the graph, if it's a pure IP, we can only use these dots because those are the only places in the feasible area where both x1 and x2 will be integers. So just to make that clear. Right, now we go on and we say, right, that was the optimal solution. So you first have to start with an optimal solution and then subdivide the problem so that you can try and find it quicker. I mean, just to explain, it's not going to be down here if it's a max problem. So I'm not going to start searching down here because I'm going to just search much longer than I really need to get to that 5 and 0. Right, so we start at the optimal solution and then break it down because that's much closer to the best solution. Purely because this is a max problem, we're then going to first get a solution for a max and then stay closely to that to not have to branch so much. If there's a min problem, you would have had the solution down here below, and then you would start down there below because your optimal solution would be there. So it's very important that you start with an optimal solution and then you work your way from there. So you don't start too far away. All right. Now we're going to say, okay, with branch and bound, what's going to happen is we can probably do solver, so open Excel as well, so long. And then we can quickly do solver to just also check later on, I think. But open Excel so long because we're going to do branch and bound simplex on it anyway. And I just want to see, we'll get to solver later. Okay, so where's my graph? I'll come back to those. Okay, so I'm going to explain the concept and then we'll get to actually do it. And then after that, we'll go to solver. So that solver is it's just an add-on if you want to check your answers. Okay, so what we're going to do. So the current answers are right now, let me just get to those answers. X1 is 3.75 and X2 is 2.25. So those are our optimal solution answers. But I highly suggest you not use solver because then you don't have the S's and the E's to work with. Right, solver is just to check, literally just to check. Right. So 3.75 and 2.25. So what's going to happen with branch and bound simplex? So now you have to listen very carefully. X1 is equals to this and X2 is equals to this. Now, there are many strategies for branch and bound simplex. We're going to focus on only one strategy, which I'll teach you. And that is a strategy of checking which one is going to find us the optimal solution quickest possible way. Now, sometimes the other way might be quicker. It's not a set in stone method. Like I said, it's just a strategy. But you have to use the same strategy as us. Otherwise, on assessment Q, it will be chaotic, right? So you have to use it. And it is there to be the most efficient way. Remember, we always want the most efficient way. So that way is actually taking the fractional parts of these values that you want to make integers. And then the one that is closest to 0.5 is the one that you're going to branch on. So write that down. So if, let's say, you had x1 equals, I'll explain this one now that's the same, but if you had x1 equals 3.5 and x2 equals, I don't know, 2.7, if you look at the fractional values between those two, which one would you pick if those were the answers? Yes, coordinates of the optimal solution. Yes, yes, yes. You have to start with the optimal solution. Have to. So which one, if you check those two that I just wrote extra? Yes, x1, 3.5. Okay, so you want to use the one that's closest. Right, so please make that note. So e.g., then you'll pick x1. But now in this one that we have, it can go either or. Why? Who can tell me why? Yeah. Same difference. Right, it's the same difference from, they're both 0.25 away from 0.5. Don't look at the integer value because then you'll tell me, no, but 2.25 is good. No, you're only looking at fractional value closest. Okay, so write that down. Fractional value closest, and then that one you pick. But if they're both the same away, we use what you've probably learned in LPR 181, which you can go through on your own about why. But we use the one of the smaller subscript then, if they're both the same. So if there was x1, 2, 3, 4, 5, 6, 7, 8, between the ones that are the same distance closest to 0.5, you choose the one of the smaller subscript. Or like I said yesterday, the most left, if you put your table in an order from smallest to highest, like we normally do automatically. So we're going to pick then x1, right, just due to the smaller subscript. Right, so please stick to that standard because obviously you're going to take a completely different route and you might even by accident miss the optimal solution and not even get any marks So please, this is very important that you follow the same. Right, so if your fractional value is closest to 0.5, that's the one you branch on. If there is more than one that is the same distance away from 0.5, the closest ones, obviously, then you pick the one with the smaller subscript. So between x1, x2, x3, x4, smaller subscript is then x1, for example, this case. Okay, so that you have to stick to. Write it down, have it somewhere so that you can work with that. Right. So x1 is the one we branch on, but it's not closer to 0.5. No, it's just because they're the same distance. So here x1 is 0.25 away, and x2 is 0.25 away. Whether it's negative or positive, that's the amount it's away from 0.5. Because they're both, not only choices though, but they're the both closest to 0.5, pick the one with the smaller subscript. Okay. If it was as clear as that other example on top that I gave, then the one that's closest, definitely that one. Smaller subscript, yes. So smaller subscript, like this one is a subscript. The 2 is a subscript, so the smaller one. Right. I hope that makes sense. Cool. Okay, so that's the idea. That's how we start branching, and we continuously follow this process. Now, guys, you're not going to all of a sudden choose a different way. You're going to keep on using the same strategy, because otherwise you'll be doing things double, or you'll do extra branches that was unnecessary. Okay, so please stick to this, do it throughout. All right, so let's see how that would work. Okay, we have to now prepare it. All right, so we use our integer programming model, and we call it relaxing the integer programming model. It sounds very nice. You relax the model. Why do you relax it? We say, we don't care about x1 and x2 being integers yet. So we relax it by saying we're not focusing on that yet. Do you see there's nothing saying integers in this IP model? Okay, we still have a lot of work to do. So right now we're just specifying where we're starting. There's no int, nothing, because we're saying we relax it. We are first going to get an optimal solution. Right, remember I said you need an optimal solution first. Right, now we get to the part that you already know, and I don't really need to tell you anymore. Do we do primal or dual simplex? Yes, all our signs are less than or equals to primal. And here we go. We're going to solve. You guys are more than welcome to also solve, but it's better to obviously focus on what I do and then later on try it. But yes, the relaxed IP is a normal LP. You're just saying, I'm ignoring the integer part, so it's a normal LP. Yes. And now we're going to solve it as a normal LP, and then after we get an optimal solution, we say, okay, now let's get back to integers. Right. So if they ever ask you, please relax the IP, you don't specify integers, because you first want to solve it without focusing on that. All right. Now we check canonical form. You add your slacks like you normally do. This is primal simplex, the Z values you take over, and we're now going to solve it. Okay. So our initial table there, I'm not going to do it slowly because you have done it before. So I just want you to focus right now. When I get the optimal table, I'll give you a few minutes just to retype it, and then you can do that with me. So primal simplex, this is a max problem. In the Z row, we look for the largest negative, which is -8. You do your ratio test, right-hand side over the pivot column, choose the smallest positive. That's our pivot row and our pivot column. So if in a test I ask you, what is the pivot column? What is it? In the initial table. What is the pivot column in the initial table? X1, perfect. What is the pivot row? Now be careful, we'll say something like constraint or row, what. But yes, constraint 2. You have to be specific by saying constraint 2. Otherwise, someone would argue and say, oh, but this is row 2. Oh, no, this is row 2 if you start with the numbers. Constraint 2. Okay. Be specific if there's nothing specified. So say something like C2, like you guys said. Otherwise, someone might argue and say, but that's not, even though logically, but yeah, please be specific. Right, then we go on, we get a new table, largest negative still, ratio test, smallest value. Okay, what's the pivot column in this case? Table 2. Or after the first pivot. X2, yes. What's the pivot row? Be specific. C1, very good. Pivot, we get our values. Now we get that 2.25 and that 3.75. Right, so you break it down into only the fractional part like I explained. The one closest to 0.5 is the one you're going to branch. But because they're both 0.25 away, we just pick the one of the smaller subscript. So between the two that we have that is actually equals to those values, we pick the one of the smaller subscript. So our winner is X1. Okay, so now we have to focus on X1. Now I'm going to focus completely on X1 for the first branch. Okay, so let me use a different color. Let's go green. So X1 is our focus. Now X1's value, now we go back to say, but what's the original value? The original value of X1 is 3.75. I showed you this yesterday already. I want to put in constraints to move away from 3.75. But I cannot just put one constraint because I have to be able to go both directions to check every possibility. Okay. So I'm going to add 2 constraints every time. So you can make that as a note. You're going to always add 2 constraints every time you branch. So this is our first branch. So you can call this sub problem 1, and that's going to be sub problem 2. Because you're going to have to note what is what. Otherwise, how are you going to ever fill in what I ask you to do? So subproblem 1, subproblem 2. All right. And no, solver you can only use to check. Right, check your answer, but you need an optimal solution of either prime or dual, depending on what was required. Okay, so call them subproblem 1 and 2. In a test, I'll probably give something away so that you follow the same process. All right, so just be very careful not to just go and jump in. Actually check what is given. Now we go and we check X1. What can we do? We need 2 constraints. So the only 2 constraints you can add is either rounding it down or rounding it up. Then I told you yesterday, you cannot go and say greater than or equals to 3 and X1 less than or equals to 4. Who can remember why not? Why can I not do that? Or why is that pointless? It won't change anything. Perfect. I mean, the value is already between 3 and 4, so it's not going to change anything at all. So please, no. All right. You want to move away from that value, to force it to not use that value. So you're either going to go less than or equals to 3 or greater than or equals to 4. So you completely move away from the value. Yes, it could turn into a 4.5, but that doesn't matter. We're checking all possibilities. But I'm moving away from 3.75 completely. Right, so that value in between 3 and 4 cannot be used anymore at all. Okay. Right. I just got a notification. Your projects for our project for LPR1, thread 1 groups will be sorted somewhere today. So it will be there very soon. Right. So if you're worried about that, it will be there very soon. Okay. If it's there, I'll let you know. Then you can tell me if something went wrong or what. Okay. All right. Let's see. So that's where the values there come from. just so you know. Now we need some time to quickly retype our optimal table. So I'm also gonna just copy the optimal table, and then you can go retype it quickly for me so that you can work with me. Obviously, if you feel you work a bit too slow, then you just watch, right? Don't waste time, because we obviously have to cover the content, so you have to then just practice on your own. But quickly type this optimal table, get ready so that we can start branching. We've got problem 1 that we need to do, and problem 2. That's our first step. We still have a lot to do, but do that quickly. Like, I'm giving you 4 minutes to go. You can do the next step as well, where you copy the table so long for the next, right? I always just say SP1, and that's going to be SP2. I should have said that afterwards. There we go. And I hope this looks familiar. Adding constraints. Just want to quickly open Paint. Just give me a second there. Okay, then I have that open. Really? Two more minutes. I'm going to continue. So make sure you number it. So as soon as you see a question in the assessment queue, they say branch and bound simplex, and you actually start numbering the same ways. So fill in while you do it. Don't do the whole thing and then come and try and fill in, because it's going to take you longer. So while you're on assessment queue, you check, okay, I need to do my first branch. Okay, I pick problem 1 and problem 2 as this. Then I go to assessment queue and I work with that, right? Right, so we go and we say, okay, we've got 2 sub-problems. Now it's like adding constraints. So we're not going to do x2 as well. We're going to get almost every possibility. So I can maybe probably show you here. Let me just do this. So if I now go from this optimal solution, that red dot, and I say take x1, and I want to either go x1 less than or equals to 3, x1 greater than or equals to 4. So what is happening is, if I look at x1 and I say 4, I'm only focusing on branching on x1, but x2 is still allowed in the values. I mean, you're just drawing a straight line. And this one is going to be less than. So it's basically saying I'm going to now try and search on that side for x1 and on that side for x1. But x2's values are also there. But it's breaking my problem into smaller pieces. And then in those smaller pieces, I'll break it down into more smaller pieces. Just to show you visually what is actually happening there. You're saying, okay, I'm moving away from that middle. That's not going to be my area where I'm going to work with anymore. I'm not going to move away from that area, moving either to the left of 3 or to the right of 4. So that's what's happening right now. Now we're in those two problems. Okay. So adding constraints, remember, if you have a less than, what do we add? If we have a less than, let's see if you can type very quickly while listening. Yes, Armandre, yes, Henry, yes. It's the third constraint we're adding because it's a new constraint, so S3. So problem 1 is x1 less than or equals to 3. Subproblem 2, you can do separately or at the same time, but let's focus on subproblem 1 quickly. So x1, I put a 1, slash 3 because this constraint is a less than or equals to, and less than or equals to 3. Okay, now we can copy this table so that we can quickly figure out what to do with that. Yes, Henry. So you're only changing the new constraint. Remember from yesterday, the adding constraints. If you missed it, please go through adding constraints revision. So we're going to go and say, take constraint 2, always top minus bottom or top plus bottom. You can always multiply something to make them the same, but they're both 1, so they're the same in terms of the number. And then you just have to add or subtract to make sure it turns out to be 0. Right, so it turns out to be 0 if it was basic, and it's now non-basic, although the x that you're adding, guys, that's the one that you have to do. Right, so it's a bit easier than yesterday. It becomes 0. What you do for the 1, you do for them all. Now, like Henry specified, you have to multiply by minus 1. The reason being, as soon as I drag it through, S3 became minus 1. I can't have a basic changing to a non-basic, so I have to sort that problem out. So that's why the formula should include, after you have your brackets, times minus, not minus 2, minus 1, so that that S can be sorted out. Right, so when you drag it, remember what you do for the 1, you have to do for them all in that row for the whole constraint. So it's top minus bottom, and you multiply it by minus 1 due to that S becoming negative. And negative 1 is not a basic variable, so you cannot leave it. Right. Your X that was basic that became non-basic is now basic again. And your S that you put in is basic. So you're sorted, and you can start doing pivots. Okay, what seems to be the problem that we have to pivot on? You did adding constraints yesterday. What's our problem? What now? Yes, C3, right. Ruan, yes, but you are only branching on 1 at a time. You cannot branch on 2 things at the same time. It's going to become very chaotic. So you only branch on 1 thing at a time. So right now we're focusing on X1. If next time we focus on X2, then it's only X2, but you only branch 1 at a time. Right, so, but if it was X2, then you'll have to check what are the conflicts there. So where's the 1 for X2 in the new one? And you subtract that top minus that bottom, which we're probably going to see very soon as well. I hope that makes sense. And then yes, C3, yes, that's our problem. Negative right-hand side, it's dual simplex. Right, this looks very familiar. Then abs, yes. But abs on what? Which values? Or tell me which columns? There are not many. Yeah, there's only one. S2 is the only one. You can only do it on negatives, right? So you'll do the abs. I'll do it for now to recap, but remember it's only one, so we really don't have to. But top Z row divided by pivot row, and you'll know smallest positive abs. Okay, but we only have one choice, so that's our choice. Let's pivot. Let's get a new table, and we hope for the best. If they have numbering as well in the tables, then you follow the numbers as assessment cue. I'm not being too specific there right now because I'm using this as my numbering. Okay. Right, let's pivot. Let's see. Some of you probably already pivoted. What's happening with X1 and X2? If you're already done, let me know. Yo, you guys are fast. I'm impressed. There we go. Z is 39, I agree. X1 is 3, yes, I agree. X2 is 3, yes, I agree. Awesome. So, do we have to branch this one any further? No. Is it the best? We don't know. We don't know yet. So, it's just right now we call this a candidate. It's an option. It's a candidate. I'll call it A. It's a candidate. We're not going to stop, right? We're not going to stop. But as soon as we get whole numbers for what we specified, we're happy with that branch. We're done with that branch. So yes, I'm Andre. So right now, we said both of them need to be integers. They both are. So we have a candidate. If we only wanted to have x2 as an integer, well, x2 is an integer. We got it. Okay. But it purely depends on what you specify in the beginning. If both must be integers, then you only stop if both are. Okay. If I specify in the question, like Anika asked, like, could it be that we specify? Yes, we could specify saying focus on only making x2 an integer. Or if the scenario is very obvious in terms of the one must be integer, or if I lead you to that, then you focus on only that one and it doesn't matter what the other one is. So if you get that as an integer, you're happy. That's the mixed. Okay. But we are not done, right? I told you we still have a lot to do. Right? This is just candidate. It doesn't mean it's the best. We don't know. All right. We have to go through the different possibilities. Right. But going for x1 less than x3, we are happy. All right. Marizon, you'll probably see very soon. Let's see what happens with the other branch. Okay. So now I just want to quickly introduce a new topic. So we have what we call backtracking, or you can do jumping between the branches. Okay, so meaning if you were to program this, how are you going to approach it? So you can either go and say, let's say if this one had more branches, so let's say x2 was not an integer and you had to go on, then you'll decide, am I going to then go on with this one and finish it? Or am I going to jump and do this one at the same time and then go down level by level? So that would be jumping in between them to do it at the same time. But if you want to do backtracking, you're going to complete one fully and then go back step by step to check what have I not done yet, and then do those. So those are just two concepts that can maybe help you program this. All right. But more I can't say. There we go. Okay, so let's add the other constraint. So side problem 2 there was this one. I'm just going to copy it there so that we can clearly see it. If it's greater than or equals to, what do we add? S or E for constraint 3? E, perfect. And I hope you guys see And because this is where it can get confusing, I like jumping rather, because then I can quickly see, oh, okay, I'm not going to have a constraint 4 because these are doing at the same level. Because I cannot possibly have x1 less than 3 as well as x1 less than greater than 4 at the same time. That's infeasible, guys. Please, it's copying the table twice and doing them at the same time, but not on each other, because it's not possible to do them at the same time. You can't have x1 less than 3 as well as greater than 4 at the same time. So it's the previous optimal table, right? Previous optimal table, but you're doing two separate problems. That's why the sub-problem helps making us realize, oh, it's not the same problem. Okay, we're trying something different, the other way around. So instead of less than, we're now trying the greater than part. Okay, so just wanted to make that clear so that that doesn't go lost. So now we're trying again, constraint 3, but instead of x1 being less than or equal to 3, x1 is now greater than or equals to 4. Now remember, in dual simplex, you can multiply by minus. I know. But you don't have to. I showed you yesterday that immediately when you do the minus or subtraction, it's going to sort the e out. So if you want to multiply with minus first, that will also be fine as long as you get the correct constraint, okay, which we're going to do now. Yes, Henry, perfect. So we're going to now copy our table and only modify this new constraint. What's my problem? x1, because that's what I'm adding, x1. Top minus bottom, we'll make it a 0. Then when I drag it through out, the e is sorted. Okay, I don't have to multiply by minus 1 or anything if I left it like that. All right, if you want to multiply by 1 first and then just make sure that you multiply again, which is quite pointless, you just have to make sure you get exactly the same constraint as me, because that's what I'm expecting to see in your answers. And obviously, you have to get the right constraint to be able to continue, right? Yes, the E is convenient for once. All right, so dual simplex again, guys. This one, negative on the right-hand side, we have to pivot. Do your abs. If there was more than one. If there's not more than one, guys, it's only the negative that you're going to work with. So pick it and go. Let's pivot. Let's see what happens to this one. If you guys are really fast, you can let me know what happened. And cry a bit when you see the problem. Yeah, Henry, do you feel the pain? The pain that we are not done? Okay, so let's see. Our Z plus P41, I agree. X1 is a positive 4, I'm happy. But our problem is X2. I'm going to make it a red just to make it very dramatic. Okay. We are not done. It's not a candidate at all. Now, just to make it clear, if we wanted only x1 to be an integer, now you answer me, can this be a candidate? If you wanted only x1 to be an integer, mixed, if we were only worried about x1 being int. Perfect, yes, then it's a candidate and I'm done. Right, then we would have been done because I don't care about x2 being an integer. Now, sadly, we wanted them both in this case to be integers. So are we done in this case? No. We have to now continue branching. So we are now going to create 2 branches for this one. Do I have to worry about choosing between x1 and x2? Do I have that worry again? Nope. If you had more variables, then you'll probably have to choose again. So just to make it clear, if you had to choose again, let's say you had an x3 that's also still a fraction, you again do that part where you take the fractional bits The one closest to 0.5, that's your branch. That's how you go on. Okay, not randomly. You keep the same standard. You keep on doing the same strategy, all right, so that you can try avoid doing things that you don't have to. You're trying to find the most efficient route. Okay, so please, if there were more options, you still have to do that whole take the fractional bit closest to 0.5, and that's the one you go with branching. Okay, we only have one option, x2, right now. So you're going to go with x2. x2 is going to be less or equals to what? Who can see what it should be? What should x2 be less than or equals to? Yes, Annika, that would be very sad. Yes, so x2's value is 1.8. We're trying to move away from 1.8. So we either go less than 1 or greater than. You can tell me? Marizon, yes, only x values to branch on, not e's or s's. E's or s's are just your resources. It helps you to figure out how much x1 and x2 can change, of course. And that's why in the new constraint, they are still added in the calculation, but you don't branch on them. You only branch on your x's or y's or whatever variables except your slacks or your x's. It's a very good question though. But yes, 2, 2, 2, because we're trying to move away from 1.8. So we got 1.8, we say either go below or above. All right, so 1 or 2, 1 less or 2 up. So this comes from, now check my numbering to help yourself. This comes from, now please, this comes from subproblem 2. I'm not going to go back and copy this original optimal table because I already modified the optimal table here in subproblem 2 with adding a constraint and saying go that side. Okay, otherwise you'll be branching more than you need to. You are now going from this problem that you're branching, you're copying that table because it's already been modified. So you're copying that table. So when I number them, you'll see I'm saying 2.1 because it comes from problem 2. 2.2 because both of these problems come from problem 2. So I copy problem 2's table that was optimal, just not a candidate. So 2.1, 2.2, to be very clear that it comes from problem 2. So I hope that makes sense to make it easier to number. All right, so this is going to be problem 2.1, and that's going to be problem 2.2. Okay. So let me just copy it, leave a space for the S or the E. That's 2.1 and 2.2. So I hope you see why I'm copying them at the same time to make sure I don't add problem 2.2 on problem 2.1 because they're two separate problems. However, they come from problem 2. I'm adding on to that. I'm going deeper. So if I go quickly back to this, problem 2, we made x1 greater than or equals to 4. And problem 1, we made x1 less than or equals to 3. That gave us a candidate, the less than or equals to 3. So if I look here on my picture, the less than or equals to 3 part gave us candidate A. But greater than 4, we got an x2 equals 1.8. So now we have to go and say, okay, x2 equals 1.8. So now we either have to break it here or here. I hope you see something's going to be infeasible. But we're now working with that small little rectangle there, trying to see if we're going to get a candidate or an infeasible solution there. We're going either to x2 less than. So x2 less than, let me use a different color so you can see it clearly. I'm now in that area. x2 less than 1, because we said less than or equals to 1, or x2 greater than or equals to 2. So I hope you see there's not much left to do, lucky for us. But that's what we left. I hope you can see which one will be infeasible. Not that I'm asking you to do it graphically, but it helps. And just in case someone puts a question like that in. So you're saying x2 is now going to go less than 1 and greater than 2. So those are our new search areas, and we're going to branch on those. But they still come from the fact that x1 was greater than 4. It's still this side. It's not on the other side. So I'm copying that table and building on that table. All right. Desmos, I'll ask, but unlikely. I don't think you... if we give you a graph, you'll be able to see it on the graph. So it's not really necessary to draw the whole thing. If it is, I'll ask, and I'll let you know. But you'll see it in the instructions, so that we will put in the instructions if I get a final decision. Right. Now let's see what's going to happen. So we copied our table twice. Now, if you already got the gist of it, quickly do those, but I'll show it to those of you who like just looking and want to first understand. So for the first problem 2.1, we're saying x2 less than or equals to 1. So we need a slack. Slack 4 because it's the fourth constraint. Right, x2, not x1, x2 slack less than or equals to 1. So now we're going to focus on that one. So I'm going to copy the table and I'm going to go and say what minus what. So let's see which constraint minus which constraint to sort out our problem. Who knows? Which constraint minus which constraint to give us a basic variable again. Perfect. Our problem is x2 because that's what we're adding. So that one and that one is problematic. It's not basic. So I have to make sure I take that constraint minus that constraint. Constraint 1 minus constraint 2 to make it a 0. And you already know by now what happens with slack. Every time you have a slack, remember to put brackets, yes, and times minus 1. Okay, so please don't forget with your slack, that's going to be the case. Okay, we've got 2 negatives in there, so sadly we have to do abs this time. Abs is a must. Z divided by your pivot row. So if you didn't do abs now you have to. Z divided by pivot row. Only for those 2 negative values, only smallest positive. Right? Although, because of abs, all of the values we use here are positives. Hint, hint with the zeros. All of them are positive, even though we seem to use negatives only. We take them as positives. Hint, hint. Okay, let's see what happens. Thank you for making it clear, Manisha. I like that wink, wink. All right, let's go. Let's see how fast I can do this. 1, 2, 3. There. No, wrong button. It's a new keyboard, so it's taking me much longer than it used to. I'll get used to it soon. Oh, Henry, are we gonna cry? How do we feel about this table? Okay, sadly, it's not a candidate. Sadly, but it's good. It's good practice. We always give very big problems, so problems that branch a lot. So it's very good practice. But what's our problem? Which one? Both? Just one? x1 is not an int. x2 is perfectly fine. x2 is equals to 1, but x1 is not an integer. We have to make both because we said both, pure IP. So we're going to have to branch. So we're going to have SP 2.1. Point 1. SP 2.1. Point 2. Okay. Now, obviously, guys, you can now decide, am I going to first go on with this to not confuse myself with this other problem? So what I normally do is I make sure that that other problem is copied and ready, so that when I come back, I don't think, oh, what was it? Was it this table? Was it that problem? What was it? I can't remember. Okay, so I already make sure that this table has everything it needs so that when I come back, I can just go on. Okay? No, you did not for marks. You did not do enough. Remember, this is all for marks, so you did not do enough. Right, so let's do the next one. All right. Now, this is not ready. This is not a candidate. No, no, no. All right. According to me, no recording. So yeah, you can ask the dean or someone, but there's, yeah, according to me, no recording. So I don't know if it's gonna be up there somewhere, whatnot. That's what I know. Right, but no, this is the average problem, or actually technically they usually tend to go much bigger than this. This is quite actually a small one, because remember, you're going all possibilities. It's us doing it manually, but technically you would rather program an algorithm like this that would do it in the background. So you set it up once and it will go through all the possibilities. I mean, with programming, you can do things much faster than this. Right. Can you stop if you get a table you've had before and the branching will be the same? Leonard, if it's exactly the same, I mean like exactly in terms of x1, x2, the z, the slack amounts, like if all of those are the same except now the new slack, of course, you won't stop. You will then say, okay, let's try, instead of that x that I branched on before, let's try a different x. It's not likely to get the exact same table, but if that happens, try the other one to see that there's maybe not a different route you can go with. Okay, maybe some other possibility that would be better. But you never stop until you found all the integers you needed to find. Okay, so in our case, we wanted both x1 and x2 to be integers, so we can't stop until they are both. Right, if we only wanted x2 to be an integer, then we would have stopped at this one. Right, if we wanted x1 to be an integer, we wouldn't stop because we still need to continue. Okay, so do you see why I mean name your problem so that you can keep track? 2.1 is going to go now into 2.1.1 and 2, two problems. But where does it come from? Which table am I going to copy? Table 2.1. So I'm copying table 2.1 twice. So that is why numbering is very important, because you're going to get confused, yes. Okay. So numbering is very important, so that you can now go and say, okay, I'm now going to have a 2.1.1 and a 2.1.2, which both comes from this one, right? So that I copy the correct table. Oh, well done, Armandre. Yeah, so we're now going to go and say, okay, x1 is our problem area. So x1 less than or equals to something, x1 greater than or equals to something. So x1 is 4.444. Now let's see if you guys can get the correct values though. What should the values be? x1 less than what and x1 greater than what? Let's see. What happens if you only have one of the xi being non-basic and then one basic? Just remember, if something is non-basic, it's just equals to 0. So that's an integer. Good question though. Very good question. Clever one, that one actually. If something's non-basic, it means it's equals to 0. So it is an integer if it's equals to 0. So that one you can't continue. If the other one is basic and it's an integer, you're happy because then technically both are integers. So a very good question, that one. All right, so what Zoe was saying there is, let's say x2 here was, let's say x1 was a 1 and a 2. I don't know, random values, but that's not basic. That's non-basic. Then it means x1 is actually equals to, sorry, wrong button again, 0. If it's non-basic, it's equals to 0. Then we check x2. x2 is equals to 1. Well, if both of them are integers, 0 is an integer, so it would be a candidate in that case. All right, so very good question. Right, but in our case, it was basic, so sadly we had to continue. All right, let me see your answers. Yes, less than or equals to 4 and greater than or equals to 5. Because the value is 4.444, you either go less than 4 or above 5. So you move away from that middle. Very good. Copy the correct table. And let's do those. Let's see. So we're going to add our slack here for this one. Slack 5 already. Yo, we're climbing. Okay, problem 5 there. It's x1 now. x1. Slack for less than equals to 4. On the other one, I just normally go and copy already what it's going to be so that I make sure I don't forget what's happening there when I come back. Okay, just trying to give you some advice as we go along because it can get really confusing. And what does help though is having a paper on the side that you write down, oh, I'm now at 2.1. Okay, 2.1 goes into 1 and 2. Okay, then I make a tick mark when I'm done with it so that when I'm finished, I can check which ones did I not tick mark or complete yet. And I go to those and I do those and I know exactly where they came from. Right? Oh, thank you. But then I know exactly where they came from. So that would help a lot. If some of you are, I know we all normally doodle stuff and that's much easier to work with. Oh, pleasure. Cool. Armandre is already there telling us what happened. Also, let's see. But you're giving us some hope there. Yeah, especially the bigger the tables, it kind of gets harder to see. And I'm going to probably also have to zoom out now soon. The bigger the tables, the more we'll have to zoom out. And then you're like, harder to see. So yeah, having a big screen is always a good idea. But it's not always possible. So yeah, zoom out a bit, but use colors. Do something that you know will help you keep track of what is where. My spacing, I gotten used to it because I've been doing it a few times already. So for those of you who haven't done this in a while, I mean, it's been a year for most of you, or 2 years or so. So for that case, you're going to have to practice a lot so you can get used to, okay, how can I space this to help me? Sure. But how can I space this to help me keep track? So I'm just used to this. You see me putting things at the same place. And then normally what I do is I make a new sheet. So when I come back to something at the way beginning, I go and copy that into a new sheet. And I just go from there so that I do not go down and all of a sudden there's another table and I'm overwriting stuff. So that's just also something that I tend to do. All right, let's see. We only have one option here, so no abs. No need for abs. Only that one option, only that's negative. So let's see what happened to this one. 1, 2, 3. This one, 1, 2. Let's drag it through out. And then we go and we divide. When my mouse does not want to move the way my hand moves. There we go. All right, let's see. So we're going to get to the best like Leonard already gave us. Leonard, you're too fast. But that's awesome, but too fast. Henry, yes, this one is 37. And Armandre, yes, it works. Are we branching? No, it works. Yes, you have to. Please, you have to be fast. But both of them are integers. So this is candidate B. We can call it B just to keep track. Candidate B. All right. And we have a solution that both are integers. We're done with this branch. Now we have to move backwards. So this is backtracking if you haven't done them at the same time. So I'm now going back and checking what have I not done. But you see why it's important to have all of this ready, this table that you already copied, so that you don't think, oh, where did I come from again? Unless if you're really good with your numbering, then at least that helps you. All right. But sometimes numbering can become confusing, even if it's on assessment cues. So already copy that table. Have it there twice so that you literally just continue. Okay, so I hope this will help. Let's see. Let's go and add a new one. It's greater than, so it's an E, -1 for your E. Yeah, we normally, if we ask tables, we ask only pieces of it. You won't fill in the whole table. You'll only fill in pieces of the table. That's if we ask table. Sometimes we just directly ask you for what is x1 and x2. The answer for x1 and x2, or just a new constraint, but we won't ask you to fill in the whole table. Unless if there's something specific we want to see. So if we ask you for the whole table, there's a reason for it. Obviously, I can't elaborate, but yeah, we won't ask you to fill in all of these values. We'll ask you to fill in what we need to see, right? In order, if there's something that went wrong, that we can see that you guys are still correct. No method marking, I'm not saying that, I'm just saying if there's something that we pick up. Right, so I'm just quickly going to do this one. Let's see, top minus bottom, the E gets sorted, nothing there to do. Henry, don't give me the spoiler. But we're going to go to 2.2. I'm just going back step by step. Right, let's see this one. Let's see how this one went. But I'm glad you're saying it. Otherwise, I would have wondered if you guys forgot, you know. But it's good, guys. You have to go to every possibility. Please remember that. Just one thing, though. If you've made a choice and you choose to branch on that X, doesn't mean you have to go back and do the other X, unless if we had that special case that I think Leonard asked about, what if it so happens to get the same table with the exact same values for x1 and x2, then yes, I would say, yeah, please try a different X, because that's not working. You're looping or something. But hint, guys, you can loop because you're choosing the zeros incorrectly. Remember, in a ratio test, if the value is 0 in a ratio test and it is a negative, you're going to loop. If it's a positive and you don't pivot, you're going to miss the optimal solution. Right? So please remember those with the zeros. They are very important. For dual simplex, if there's a 0, you have to, because we take it as a positive. Remember, I told you the abs, we take these values technically as positive. So if it's a 0, it's a positive. Hint, hint, my wink, wink. Okay, so this one also, both integers, so we smile because we don't have to branch this one again. We're happy with this one. Both of them are integers. This one gave us candidate C. It's C. All right. Now, Henry, it's your moment to shine. We need to still do which problem? And Manisha, yes, it's the 5 and the 0, which we wanted. We finally got that one, but we don't talk about yet, right? But yes, I'm glad you see it before I say anything. But we need to still please go back and make sure you didn't miss anything, right? We didn't do problem 2.2. Right. So in this case, I would have copied this into a separate sheet, but I've got space. So I'm going to just put it there because we already know it's infeasible. But we have to prove, we have to show, because you won't always know straight up that it's going to be infeasible. So please, you have to first do it and show. So this one is x2 greater than, so E greater than 2. So it helps having the table and everything ready so that I don't have to go and figure out, but what did I want to do here again? Which table did I have to copy? I can immediately just go and say, sort out that conflict. Is the E a positive one? Yes. Now, Henry, your moment to shine. Why is it infeasible? I see others also typing. They're like, no, I'm taking Henry's moment. Okay, Henry, you were quick enough. There are no negatives in the row where you've got your negative 0.2. Perfect. Right, if there's a negative that you have to pivot on, then you're like, okay, I have to pivot. It's still simplex. But now we go inside and we see no negative. So there's no, yes, Conrad, no pivot column. So we have to then specify this is infeasible because we won't be able to do anything with this. Okay, you can't continue with this one. Right, it's infeasible. If you see infeasible, you say yay because something is eliminated. Something's gone. Right. Right, in a test, we might ask you, what are you branching on? You can specify constraint 4, or it would have an option saying infeasible. But when it comes to the column, then you'll have to specify it's infeasible. Like there's no column. So I like that Conrad said no pivot column. There's no pivot column. It's infeasible. There's no pivot column. Okay. So if we ask, then you have to say there's no column. It's infeasible. Okay. Did we branch everything though? What do you guys think? Did we branch everything? Thank you, Felicia. Yes. So if I just go through the slides and show you the final one there. So the final one there, just to show you, we went and we branched, and just to show you how you can draw it on paper, just to have your quick reference to see, oh, that's infeasible. That one we had to continue branching. We had candidate A there. When we continued, we had candidate B. We continued and we had candidate C. Right. I was wondering what happened there with the all caps. I will show you now, just now. So candidate A, we had that infeasible. We had candidate B and candidate C. And then we just have to take note of what were the candidate values. So between all of those, so that we can specify which one is the best. Now, who can tell me why is 40 the best? Just to make it very clear before I go back to the infeasible one. Why is 40 the best? Yes, it's the largest value for the Z, specifically the highest value for the Z. Doesn't necessarily have to be an integer, but your x's are integers with the highest Z value. That's perfect. That's very specific and nice. So your values are integers, which is what you wanted, and the Z is the highest. Why should it be the highest? Very good, Christian and Michael, and there's a few of you said it. Highest profit, because you wanted to maximize the profit, right? Max problem, so you want the highest. If it was a min problem, you would pick the smallest one, right? But it's a max problem, so you have to pick the highest one. Min problem, you do exactly the same, just pick the smallest one instead then. All right. And then, Armandra, you asked me just to see the infeasible. Just want to go this one. Do you want me to do the calculation as well, or do you just want to see the values? Okay, cool. Great. So guys, obviously you need to do this on your own. If you just watched, you have to do this one as well on your own, just to practice. There are exercises to do as well. I just want to quickly run through the mixed, not fully, just run through the mix so that you understand what should be done, and then you can later on go practice. Right. Usually it's only 2 hours because you've got 4 tests, so it's usually 2 hours or 2.5. But it's highly unlikely to be 3. So that's, yeah, you have to work fast. So fast is your level of difficulty, if I can say it like that, for this one. Okay. Your motto. Rishkar saying, beginning we start with x1 constraints because it's the smallest subscript. Yes, because they were the same distance away from 0.5. But later on, we used x2 due to the fact that every time you get to a table that's optimal, you have to check what is not an integer. So in our previous tables, like, for example, Where's that x2 one? This one. So in this table, x1 actually was an integer. So there's no choosing or anything. You only have x2, that's a fraction that you have to then branch. x1 is perfectly fine. There's no branching it. It's an integer already. If both of them were still fractions, then you have to do that whole thing again. Take the fractional part, check how far from 0.5. So if x2 was 0.3 and x1 was 0.2, we would have started with x2. Yes, because it's closest to 0.5. Yes, perfect. They're the same distance, then smaller subscript, 100%. All right. Yes, I think also that's a difficult part, keeping track and making sure you copy the right tables. True, very true. Okay, let me see. So there are exercises I just want to quickly show you. Let me just open the Oakland. So in the Oakland Corporation, there's a mixed IP1 just to show you what would happen, right? So I'm not going to do it slowly. I'm just going to show you. So in this one, they didn't want both of them to be integers. So they specified specifically in this one that x2 should be an integer only. Right, so they went in the IP here and they said only x2 needs to be an integer. So I would specify, or the scenario would be obvious for you to know exactly that that one or those, because there could be more, should be integers. Then those are the ones that you look at. You choose between only the ones that should be integers. In this case, only the one x2 should then be an integer. So even if x1 is not, there's no checking. It's only x2. All right, so Rishkar, no. Then you don't check. If you do, however, have more variables, so Rishkar, and if you had x1, x2, x3, and x4, just for example, and we say x2 and x4, we want to have integers, then every time I'm just going to be looking at those. The other two, whatever they are, I don't care, because we don't worry if they're a decimal or an integer. We don't need to worry about those. So then you'll only work with those two. So if them both are not integers, you do that whole check. Okay, if x2 is 2.5 and this one is let's make it 3.7, the one closest 2.5, I branch on that one. Okay, yeah. Cool. But yeah, for mixed, definitely less tables because you're not worried about all of the variables. Definitely less tables. So you'll see now if we say x2 must be an integer, we don't worry about x1. So there's no choice. We just go with x2. So we go to the optimal table. But remember, you need an optimal table first. You see that part? I didn't do it because, I mean, it's still the same scenario. Optimal table. Check your values, but do I need to check the fractions? No, because we only need x2 to be an integer. So I only focus on x2. 2.25, I either go less than 2 or greater than 2. I have my first two problems. Like I said, every time you're going to have two problems. You're either going to go less or above, but you're going to have two problems. Right. Armando, I might like you, but with regards to tastes, I want to see that you know your work, so probably not. I can give you the hint. If we ask you mixed, it's probably because the pure is just way too long for the amount of time you have available. So I won't give you something you cannot complete if you practiced. If you practiced and you work fast, you will definitely complete the whole test with all the topics we will be doing. Don't worry. But if you don't practice, guys, and you have to sit and figure out what to click and what to pivot and and then you're like, oh, which table? If you have to get stuck somewhere, that's going to eat your time and you probably won't finish. Okay. So when we get to the next topics, you'll start realizing which topics you feel more comfortable with. Start with those. You don't have to start with question 1. Start with those you know you can do faster. Do that, finish. Next question, which one can I do faster? Do that, finish. All right, so that you can have time for the questions that you feel like you can make mistakes more on. Okay. Just advice, obviously, for any test that you guys write. That's usually the case. But I'll check your chats now just to make it clear. You have your 2 branches. In this case, they were both finished. There was no more branching. And to make it clear for this side, x2 was an integer. Even though x1 is not, that was not the problem. We just wanted x2 to be an integer. So this one's done. On this side, they're both integers, which is even better. But it doesn't mean that this is the best solution. So please take note of that. The best solution is still the one that would give you the max or the min. This is a max problem, so I want the one with the highest z, whether it's a fraction or not. Z is just profit. I don't care if it's a fraction. So which one would give me the highest value is this one. So that's my best solution. All right, best solution, even though x1 is a fraction. And it's perfectly fine because we only wanted in this scenario x2 to be an integer. Okay, so I hope that's clear. You guys okay? Oh, no more questions, but are you guys okay? Manisha, you're okay? Nice. Who else? You okay? We good. Good. Okay. Guys, please don't feel stress or anything about asking me just to show a table again or just to quickly scroll up or something. I mean, if you need to see something, ask. Right. Am I good? I guess. It's a nice subject. So I'm enjoying this with you guys, and you guys are working with me, so it's quite fun. So I'm good. Just the afternoon I get tired, then the other class is quite tiring. No, nothing's a dumb question. Nothing's ever a dumb question. If we are solving for a min z, when all the coefficients in the objective function are negative and there are no negatives on the right-hand side, then we have reached the optimal solution. For min problem, no negatives on the right-hand side. Objective function, when all of them are negative. Yes. That's very true. When it's a min problem, we always pivot on the z row on positive values, so there should be only negatives in that case if it's a min problem. And for the right-hand side, whether it's a min or a max, there should be no negatives. Very true. Very true. Okay, so right-hand side, no negatives whatsoever. If it's a negative, it's not optimal. If it's a max problem, there should be no negatives. If it's a min problem, there should be no positives, right? Because you pivot on the largest positive, definitely. Right. If the change of the mix, we only focus on that variable that has to be integer. Yes, you only focus on that, but just like I showed you here, you can have more than 2 variables that should be integers. Then you focus just on those. So whatever else you have, they can be whatever. But you just focus on the ones like x2 and x4 here that you want to be integers. So you keep on focusing on those. So if, let's say, you had these 2 that should be integers, you focus on those and you get to a step where they're both fractions, you do that whole checking again, that whole which one's closer to 0.5. If they're both the same, smaller subscript, that whole thing. Okay. Rishkar, no, when you get to branch and bound in there, okay, technically yes. We get to branch and bound, we normally just do dual simplex, but I'm really glad you brought that up. Guys, please always check that it's optimal. In most cases, it does nicely work out to say if you do dual simplex, it's already optimal. But what is very important is you remember that dual simplex has 2 phases. So it's not always going to be optimal with every time you just do the negatives and they're gone, right? So that question was very important. If it's a max problem, you do that negative, you still have to check the z row for the second phase. Max problem, we had to make sure we pivot on negatives, largest negative, to get the negatives away. So in this case, when we get to this branch, we like immediately see, oh, it's optimal. I don't have to do a second phase. But if there was a negative here, I can't change the formula, but if there was a negative 5/9 here, I would have to pivot on that S3 and do the ratio test here on the side. Primal simplex. Right, remember phase 2 of dual simplex is primal simplex. That's why you have to be 100% of dual simplex. Right. After you get the negatives away on the right side, you have to do primal simplex. Min problem, pivot on the largest positive. Max problem, pivot on the largest negative. Okay. So that's the part that changes, the second phase. Luckily, with most of the branches, it's immediately sorted out and you don't have to do the second phase, but please check, just in case there's a pivot. Second phase is primal simplex. Right. We tend to forget because there's so many branches. So please check that. Okay, so we're going to take a quick break and then we're going to do the next algorithm and then I'll give you a chance to practice a bit, right? Because the next algorithm it's complicated but short. All right, so I'll give you until 10:15. So I'll see you again 10:15. I saw some students talking about PM and AM. This specific session is AM, and I'm not aware of any PM session for LPR 381. So you'll be writing in the morning. So at 8 o'clock. But just check the dates on the study guide. I'll still confirm with you about the second due to the career day. So that test will probably move if it's going to be at career day still. So I'll let you know about that one. But remember, the summative is definitely not on the Friday because of the public holiday. But the rest are still as on the study guide for now until I let you know. Right. But morning session starting at 8, webcam on, the usual, the drill. Webcam on, start at 8, go to assessment queue, get ready, be here on HypeFlex so that with your webcam on, so that I can obviously invigilate you or whoever is going to invigilate you. And then you start an assessment queue. Okay. I've been talking and I don't even check if you guys can hear me. Can you guys hear me? It's so good. Okay, cool. Otherwise, I've been telling you all this and no one actually hears me. That would have been horrible. Okay, I'm gonna close this one. And this one. And obviously do the exercise later on, but I'm gonna close this one. So cutting plane. Rishkar study guide is on Moodle, BC Connect, Moodle. All of the stuff that you need is there, even the study guide. It's usually under the overview tab. Where was I? There we go. Let me just say from beginning. When I'm done with this, I'll quickly just recap Solver, and then afterwards you can practice. So that if you're good at Solver, then you are more than welcome to continue practicing. All right, but let's continue with the next algorithm for today, and then we can do that. All right, how to not go to power saving mode. What now? Rishka, I saw in the email that they said they added you. Just reply to that email if you still don't have access so that I can check. If I'm not mistaken, they did include you in the email. I can maybe see. Yeah, you are CC'd in the email where it says you've been added to both. So just reply there if you still don't have access. Right. And be specific, like say what specifically. So if you have access and you don't see the course, or do you not have access at all, whatever. Okay. If any of you don't have access to anything, you have to first check with Mr. Walgemoed. You can CC me so that I can keep track if I need to add you somewhere, but I can't add you without permission. In some places, I can't even add you. Whoever is struggling to have access somewhere. So Mr. Walgemoed would be the person to contact. But first, just check that it's not something to do with fees or something at admin that you have to sort out first, right? Because they tend to block if something is outstanding. Just want to make that clear so that I don't have to repeat that. Then I also saw a question about having LPR 3, but you still had to do LPR 2 recently. Just send an email. One of you, I'm assuming it's a few of you, just one of you decide to send an email and email that to Mr. Walgemoed asking that there's a few of you and you're not sure if you should continue with LPR 3 or if it's okay or not. But you probably saw already now that it was only small topics that were not too difficult yet. So, and you did the subject, so it should be okay. But I don't know if you're going to then, if you fail, be able to continue. So that you should ask. I do not have the answer for that. You'll have to ask for Mr. Walgemoed on that one. But just one of you ask, and then you can report back to the others. Okay. Yeah, question for ChatGPT. I like that. That's funny. But yeah, you have settings that you can search for, you know. Okay, someone else will have to answer about INM that I don't know. Right. Okay, but if there's any scheduling issues or stuff, remember Mr. Walgemoed, you can email him and just be specific, explain what you don't know and what, okay? I hope you mean jumping jacks, Amandre. I should not be laughing at that, but that was funny. Thank you for that one. You guys did not hear me laugh. Okay. Anyway. But that's nice. I wish I could be on a treadmill or something while giving class, but I think you guys are going to get very frustrated with me sounding out of breath and be like, so cutting pain. All right. Okay. But anyway. Yeah, that works, but when I have to write or something, it feels a bit awkward, or type something. And every now and then I'll try it. Thanks for the advice. Calculated error, yes. Something like that. Okay, but anyway, let me continue. You guys are too funny for me now. Anyway, we have to do solver as well, so we have to continue. Okay, cutting plane algorithm. So it's also an algorithm to get integers. It's just following a different method. It's a different algorithm. So in a test, if we ask you to get integers, we are going to specify which one to use. In your first test, guys, you can expect them both, right? You can definitely expect both branch bound simplex as well as cutting plane, definitely, right? But if nothing is specified, either or is fine. But I mean, on assessment queue, we have to let you fill in stuff. So yeah, we will specify then. Okay. Take note, cutting plane is more of a, we call it, it's not exactly a heuristic, but it's more of a heuristic algorithm. So what that means is it's like a shortcut way to get a solution quickly. Doesn't always give you the best solution though, but it can give you a solution very quickly. Okay. A lot of cases it will give you the best solution. We don't know necessarily, but it might give you the best solution. But in some cases, you could be doing this algorithm for longer than what it would have taken you to do branch and bound simplex. So it's both of them would be good methods to use. It's just cutting plane is a bit risky because you might not get the best solution, right? Whereas branch and bound, you're going through all those possibilities, so it's very hard to miss the best solution. Whereas this one, you could miss it. In most cases, you will get a good solution, but maybe not the best. Okay. But it has its value. I mean, sometimes you just want a good solution and be able to continue with, let's say, maybe sensitivity analysis, which you're not doing now, but it could be a way forward. Okay. All right, we're going to continue with the same example, the exact same example. So the IP is exactly the same. The relaxing part is exactly the same. Remove the integer, you're relaxing the IP, so you're not worried about integers. Canonical form for, in this case, primal simplex, because it only had less than signs, get an optimal solution. Okay. Now, what's different from the algorithm is how to create the next table, but not the choosing part. So the choosing part is going to be exactly the same. So choosing part exactly the same. You take the fractional values of the values that you want to make integers. So we want both x1 and x2 to be integers eventually. So whatever we do, we have to then check their values. So this is 2.25 and this is 3.75. Take only the fractional part, the one closest to 0.5. That's going to be what we say cut on. If they're both the same, the one of the lowest subscript. So in this case, x1, so we're going to cut x1. Right, but cutting doesn't have two problems. It's you cut away a piece of the search area and you go to that piece and you continue. There's no up or down. It's literally you cut away a piece. So you're basically creating a new constraint that will cut away a part of your search area. So where can I write this? Let me write it here. So for cutting plane, or let me write it there. For cutting plane, you basically create a new constraint. It's not going up or down, just one new constraint. Not two new constraints, one new constraint. And you keep on building one new, until you get everything integers that you wanted integers. Okay. For branch and bound, you had two new constraints every time. Two, until obviously every single possibility was branched out. Cutting plane, only one new constraint every time. Okay. Doesn't make it easier though. You'll see now it's a bit tricky to make that constraint. It's not as simple as branch and bound simplex. But let's see. Okay, so we're going to cut x1, meaning I'm going to create a new constraint to force x1 to, how can I say, become an integer. So I'm going to cut a whole piece away to force it. But how do we do that? So now we have a few steps that we have to do for cutting plane. Okay, that's our optimal table. So remember, again, you need an optimal table. So I just copy that optimal table. Right, now this time I'm going to write it, and then you can just put in the actual values on Excel, and then we can work from there. But you're adding a new constraint. Now the new constraint, if you can figure out how to make nice formulas on Excel, I mean, go for it. But there's steps involved that I want you to know what the steps are. Right. So the first step is to highlight the one that you are cutting. So we are cutting x1. So you look at where is it basic, where's the one for the basic variable. So if I look at x1, the one at the basic for the basic variable is in constraint 2. So there's a 1. So I'm going to highlight this row. Okay. We're only looking at these two for integer values for now. Yes, for now. The Hungarian algorithm is more of a kind of an algorithm that already works with integers, most likely. So yeah, for now, these are two. If we get to week 3, then we can have different algorithms we can use, but specifically for integers, yeah, we're using cutting plane and branch and bound simplex. There are other algorithms for binary or combinatorial problems, which we're going to do as well, but that's only later. So for now, yes, only these two. All right. I'm under choosing constraint 2 because we're cutting on x1. Why are we cutting on x1? The same as branch and bound simplex. You do that whole checking. All right, the whole checking, which one's closest to 0.5, smaller subscript if they're the same. That's how you choose which one. So now I say choose x1 again, like before. And then I go to my optimal table where the 1 is for the basic variable, the one that I choose, because I'm choosing x1, I'm checking the basic variable, where's the 1? And that's the row that I'm going to work with. Okay, I hope that helps. So basically, you're not going to rewrite that. Okay, so what's the coefficient that I would put in front of x1 if I write it as a constraint again? Who can tell me? What's the coefficient of x1? Yes, it's just 1x1, right? Because these values are the coefficients, all right, if you were to rewrite it from the table as is. Okay, so you've got 1x1. Do I have anything for x2? No? You can write 0x2 there, but it really doesn't matter. I mean, here it's a 0, so you don't have to write it if it's 0. Anything that you see 0, skip. Right. No problem, Rishka. You only saw now that it's only this row, right? Next value, we've got for S1 specifically, we have negative 1.25, S1. Make sure you specify what it is. Don't just write negative 0.25 because then I'm just going to add everything up and not know what I'm doing. Okay, what's the value for S2? (0.25) S2. Yes. And then now be careful for this one. The right-hand side is supposed to be on the right-hand side. It's a constant that you're setting it equals to. Right, so it's equals to the right-hand side, which is 3.75, that value. Right, so please, your right-hand side is actually on your right-hand side because you're saying all of these values, if you were to go to your optimal table and just check the answers, x1, you check where's the basic, and you're saying x1 equals the right-hand side, equals 3.75. So whatever is here is on the right-hand side of your equals. So just to make that clear. So it's equals to the right-hand side. Okay, so your first step is to write the constraint, the values as a constraint. Now we have to modify this constraint to make it, how can I say, cut away that piece. So your first step is to split. You can say step 2 if you want to. Split integers and fractions. So basically what you're doing is you are making sure that if you have a value, you split it up into an integer as well as a fraction. Now for 1x1, there's nothing to split there. It's an integer and the fraction is 0. So in that case, you are more than welcome to write it. It's just quite pointless. I mean, you're going to say 1x1 plus 0x1. That's very pointless. So if it's already an integer, there's nothing to split up. It's already an integer, nothing to worry about. The 0x2 I'm going to remove because, I mean, it's just 0. It's not going to make any difference to anything whatsoever. Okay. Now, the other three values are not just integers. So now you have to focus on what do we do with those. So I'm going to start with the easier one. So I'm going to start with S2. I'll explain what to do with S1 very soon. So if S2, sorry, 0.25 S2, it's a positive 0.25. So I split that up. I literally split it up into what's the fraction value? The fraction value is 0.25. But what's the integer value? It's just 0. 0 S2. The zeros you don't have to write, but as you're busy with it, it does kind of help to see the steps. So it's a 0, and what's the fractional part? It's a 0.25 or 0.25, but write the 0 just to make it clear. So if you add those two together, it still gives me the original value of 0.25 specifically for S2. Okay, so that's how you split it up. I'm going to still show you the next. Now let's try 3.75. So if we try 3.75, I'm now going to work with green name. So 3.75, it doesn't have a value, a variable, because it's just the right-hand side. So everywhere where you don't see a variable, you know it's the right-hand side value. So if I split it up, it's going to be a 3, and I can't just press Control Z on this, sorry. 3, and the fractional value is 0.75. If I add 3 plus 0.75, it should give me 3.75. Okay, so if I split them and I add them back together, it should give me the original value. Right, so please, it needs to give you the original value you had before, which should kind of give you a hint already what to do with the next, but there's a little bit of a trick with negative values. All right, just want to quickly write that there. 0 is 2 plus 0.25 is 2. And then it's equals for now. And then red. Okay. Yes, please, everything needs to be split that is a fraction or that has a fractional part. Everything. Okay. So here you're not focusing on just x's, you're focusing on your slacks and your right-hand side because those will determine what you can do with your resources that you have. Okay, what do you still have available, if that makes sense. Right, S1 is now the tricky one. Right, so S1, I'm going to show you a bit slower. So with S1, it is a negative value. Now you have to make a note for yourself. When you split it into integers and fraction, the fraction at this step, just at this step, must be positive. Just at this step. Okay, later on it can change, but at this step where we split it up, the fractional part must be positive, no matter what. Okay, so now I want you to quickly think, how can I then split that up? It still needs to remain negative 1.25, but it must be a positive fraction, and whatever should be added to that to get the original value. Think about it quickly. You can do anything with the integer as long as it gives me that original value. Yo, a lot of people typing, sure. Fractional part must be positive, no multiplying, no. But it's a good try, but no multiplying, no. Otherwise, what you do with the 1, you have to do for the whole constraint. Then you're changing the other fractions to negative. So that won't work. But it's a good try, though. Vian has something going on there. Guys, check the comment we are made. Okay, so very good for those of you not catching on. If you don't, let me show you. So you're not going to use 0.25 as is because it will not work that well. Okay, so what you do is you take your integer to the next value. So you take it down, right? So you're going to take your integer to the next value. So -1, you're going to take it to a -2. If it was -2, you take it to a -3. If it was -3, you take it to a -4. Just take it to the next lower negative value so that you can add a positive fraction to get back to that original value. Okay, so -2 plus what will give me -1.25? 0.75. Very good for all of you that got that very quickly. That's so awesome. 0.75. Right, so with negative values, it's a bit different. And like that you guys gave the suggestion of multiplying by -1, but just remember, if you multiply the 1, you have to multiply everything. And then you're changing all of the other fractions to negative, so that won't work. So we have to go this route to say, to make it a positive fraction still, we take our integer value 1 down, and then we add the difference so that our fraction is still positive. Right, so that's what you're going to do with your negative values. Okay, so make a note whenever you're at this step where you have to split it into integers and fractions. If that value was negative, take the value to the next and then add the difference. Okay, so that is going to be -2 is 1 plus 0.75 is 1. This is all for is 1, obviously. Okay. I'll show you one example, like an e.g. example. Let's say, for example, I had Paint open somewhere. Sorry, let's say the value was -4.6. Let's make it, I don't know, S3. Well, how would I split this up? Let's see if you got this. Positive fraction, something to add. So the fraction must be positive. Yes, so it's going to be -5. You go 1 down, and then you add the difference. Right, -5, you add the difference. I'm wondering what happened there. Yeah, that's okay, sorry. It's an S, not a 5. But if it was, yeah, that's an S3. So S3, I should have made it a better subscript, sorry. It's an S3. Maybe writing it in a different color might be a bit more helpful. There we go. That looks a bit better. Okay. But yes, plus 0.4 is 100%. So you go to the next integer value and you say, what do I add to get back to -4.6? So if I add 0.4, I get back to -4.6. Okay, so every time you have a negative, that is what you're going to do. I hope that makes sense. Give me a thumb down if you want me to do just another one there. Thumbs up, then I'm going to smile and continue. Okay, I'll do another one. So let's say, so this is just e.g., hey? It's not part of the one that we're doing. So let's say for another example, if we say negative, I don't know, 12.75. Let's say this is E4. I'm just using random variables because I don't want it to match the scenario. So what do? Take the integer part, go to the smaller integer, so 1 down, right? A negative down. So you're going 1 down, so that's going to go to -13. Perfect, Rishkar. That's E4 still, because you're just splitting it up. It's the same variable, just splitting it up. Yes, very good. So then you're just checking, what do I add to get back to -12.75? So I need to literally add something for E4, which will make my fraction positive. So I add something to make sure I get back to that original value. So if you go and you say negative 13 plus 0.25, you'll literally get negative 12.75. You might need a calculator or just do it on Excel to help you get the correct value. Because plus 0.25, then you know if you add these two up, it's going to give you the original value. Okay. So you always go one down of your integer, and then you check what should I add to get back to the original value, so that the splitting didn't change the value. It didn't change the value at all. It's just the fraction is definitely positive, which is required for this algorithm, and it's still the same value, right? But your fraction is positive. That's your biggest focus there. So always your integer, go one down, and then obviously add whatever is necessary to get the original value again. You guys can quickly take a photo if you want to, if this might help you just to remember what to do here. If it's negative, only for negatives. Guys, positives, the fraction is positive, so you've literally just split them. Okay. Which car are you saying? Plus 1 on the left side of comma and negative 1 on the right side. I'm not sure what you mean there. Yeah, sometimes typing is a bit harder to communicate. Right? Okay, I'm sure you took a photo already if you needed to. Okay, so but positives, guys, you're literally just splitting it up. You saw there with the S2, you're just saying put the integer on the left and the fraction on the right, both positive. But if it's negative, you had to do this whole step of, okay, next negative value, add the difference. Next negative value, add the difference. All right. Yes. So if it was a negative value only though, but yes, if it's a negative value, well, yeah, you can say subtract 1. I think add 1 might make someone think, oh, minus 1, you add 1 becomes 0. So be careful with your wording there. But you go one more down. Yes. One more down, and then the right side, you go check what you can subtract. Oh, I might understand what you mean. I understand, Rishka. Yes. So if you want to do it on your calculator quickly, you literally go and use a positive, and then you just subtract 0.25 and you check the difference. That is very true. Yes. Now it makes sense. Okay, let's see. What's the next step? So if you want to write down steps, I can't remember if I made steps here. So you can say, let's say, step 1, write constraint down. Constraint down. So you're writing it from cut. Remember, you had to choose which one to cut, right? So you choose which one to cut and you write it down based on which row is the one in for that specific one that you choose to cut. So we chose to cut x1. So I check in x1, where is the 1? You will only use basic variables because those are the ones that would be fractions, right? So where's the 1? And then you highlight that row, and you can now write it down. Step 2, split into integers and positive fractions. That's a must. So we already have 2 steps now. Can you erase the bottom here? right, now we get to the next step. Okay, so the next step, you are going to actually write all the integers on the left and all the fractions on the right. So you'll see there, even in the steps, eventually it gets to a step where integers on the left and the fractions on the right. So step number 3, move integers left. We're trying to get the correct signs, and fractions right. You can make the steps a bit more neat and nice, but we're going to move them now. So 1x1, it's already on the left. It stays as is. Okay. Andre, so we doing it just based off of, we said we're going to cut on x1. That whole checking part like branch and bound simplex. So you check which one you're going to cut by doing that whole 0.5 thing. And then once you decide that, you say, okay, I'm going to cut x1. So I'm checking on x1, where is the 1? Okay. Same as, yes, same as branch, yes. Oh, sorry. Okay, so let's see. x1, it's already on the left for the integer. Now we look at this one. The integer is already on the left, so it stays there. But the fraction is not on the right, so I need to move it. What will happen to it, guys? What will happen to that fraction? Will it stay as is? What happens when you take something over and equals? Negative. So that one will become negative 0.75S1. Perfect. Okay, so done, done, done. Next one, the 0 is 2, even though 0 doesn't make a difference, but we'll write it just for now. 0 is 2 is on the left, so we keep it there as is. The next one we have is now the 0.25 is 2. Take it over. What happens? Does it stay the same? No. Yes, every time you take it over, the sign changes. It becomes negative. I'm running out of space there. Okay. Now on the right-hand side. Now I'm on the right-hand side. So the 3, it's not on the left, so I have to take it to the left. The sign will change. It becomes minus 3. The 0.75 is where it is supposed to be. So we just write, sorry for the ugly mess there, but plus 0.75 because it's already on the right, so there's no taking it over. So you'll see that's where we are now with these. Okay. Okay, next step. So this is purely just taking it to the left, the integers, and taking the fractions to the right. Change the sign when they go over. Now we're at step 4. This is the best step that you're going to enjoy. Remove left, or basically remove integers. So we're saying delete. Delete the left. So you're basically now left with, sorry for that horrible negative, negative 0.75 is 1, negative 0.25 is 2, plus 0.75. That's what you're left with. Okay, I'm just giving you some time to make notes. So it's just part of the algorithm that you're never going to use the integers ever again. Making this new constraint, you won't use the integers. You're just focusing on the fractional parts. But we like to have the fractional part in the previous steps to make sure that you get the correct fractional part. Right. Yes, I can. Read it. Move integers left and fractions right. So you can write it a bit better there. I just wanted to keep it quick. That's way more pronounced. That's S's, eh? S's. Oh, it's just taking integers. So if you check the x1 is an integer, it's on the left, we leave it. This one for s1 minus 2 is an integer, so we leave it on the left. S1 with the 0.75, that's a fraction, and fractions are supposed to be to the right. So you have to move it to the right. And if you go over an equals, the sign will change. For the 0s2, it's an integer, so you check, is it on the left? Yes, leave it. This one, 0.25, it's on the left, but fractions should be to the right. So move it, and the sign will change. Now we go to the right. What we had on the right, the 3 is an integer. It is not on the correct side, so we have to move it. We change the sign. This one, it is on the correct side, so we leave the sign. Okay, we don't take it over. Does the order matter? No, you're going to put it in the table underneath the correct headings. You're going to copy this optimal table and put it in. Right. Oh, okay, Glenn. I was like, oh, wait. So it's negative 0.75 S1, negative 0.25 S2, plus 0.75. So you'll see there they are. Okay, this one. That's why I also have it there on the slide, so just make sure it's there. Okay. Right, now the last step. Well, I would not say the last step, but you can do this step, 2 things in one. So step 4, set less than or equals to 0, then move constant to where it belongs, to the right. This is all to make sure we have the correct signs, right? Oh, you mean the order in terms of, well, not really the order. You mean like, what if your stuff was written the other way around? Like your right hand side is not on the right. Okay, no. Let me see again. All right, on the right, 7.5. That's before the 7.5, which means already there. So it becomes, yeah, that's perfectly fine. Yes. You just have to make sure that what you put on the right hand side is actually the constant value when you started with step 1. Other than that, if you move it around, whatnot, you just have to make sure you have your variables with, so you know what goes where. So when you put it back in a table, the value for S1 needs to go to S1. Right, so it doesn't matter the order when you write it down, but when you put it in your table, the value of S1 needs to actually be under S1. Okay. Step 4, set it less than or equals to 1. Always less than or equals to 1. It's to make sure whatever you do to your slacks, do not go over the amount that you set for this right-hand side value. Because slack is always less than. You're always working with less than. So even if you get an excess, you still work with less than to make sure that that difference still does not go over that amount that I want to work with. Because you can have slacks and excesses that kind of cancels them out, because you have one that's going to be a positive and one is a negative, and it's going to subtract each other. But you always just want to make sure that it's less than or equals to the value that you're going to have on the right eventually. So to show you what I mean, you're going to take that now that you have, and you're going to set it literally less than or equals to 0. And then you just take the constant and you move it to the right, because that's the only thing it should be on the right hand side when you put it back into your table. Remember, if I want to put this constraint here into this table, the right hand side needs to actually be on the right hand side. So I have to actually move it to the right hand side to be able to. Now it's a bit confusing with that whole equals in the beginning. So when you delete that, the integers, you actually delete the sign as well. So please take note of that. You delete all of it. Okay, you just left with the fractions. Then you set it less than or equals to make sure the change stays within what your resources are capable of. So less than or equals to always 0. So then we have to put it back over to make sure that the right-hand side is actually going to be on the right-hand side. So when I take it over, it becomes a negative 0.75, but it has to be on the right-hand side. So just to show you where we're going with this. Okay. So our final constraint right now is literally negative 0.75 S1 minus 0.25 S2 less than or equals to negative 0.75. Now it's like adding constraints like you always do. What variable do we add if we have a less than or equals to sign? Yes. So we're going to add like a normal constraint now. Okay, so I'm just going to quickly open any one of them. We have to copy our optimal solution. Remember, it's not the same algorithm. Don't go and copy some random table in branch and bound simplex. It's not the point. It's a different algorithm, completely different. You copy the optimal table that you got with primal or dual. Okay, why am I saying or? Because it depends on your IP. I mean, all of this was less than or equals to, so we had to do primal simplex. Right, so you copy your optimal tables, which you guys also have, so optimal table. And we're now going to add that new constraint. So we're going to literally add that new constraint. All right, let's see if I can quickly just... And that did not include that less than or equals to perfectly. Let me just do this. It's a little bit better. Okay, let's see. So we want to literally add this. All right, so a few steps to get there though, but after that you'll see you're going to smile. There's no two constraints, it's just one constraint that you're adding. So you take your optimal table, you add your new constraint. Remember, it's less than or equals to, so you please don't forget this. I see a lot of people not adding the slack. And then later on, when you actually have to pivot on that slack, you don't have it. So please, you have to add this slack every time you cut. Right? Every time you cut, you're saying less than or equals to 0. Every time. So every time you're going to add a slack. Every time. Okay. Nothing. At S1, you put a negative 0.75. At S2, you put a negative 0.25. I don't know why I'm saying equals. And there you put a negative 0.75. And now you can do dual simplets. Quickly try if you have done it on your own as well. So negative to pivot on. We do our adds only for the negative values. Z divided by the pivot row. We drag smallest value. There we go. And let's pivot like we always do. Okay. So I'd usually call this a new table. I would say something like table 4, just so that I know, okay, I've done something. This is now a new table that I'm working with. But keep checking assessment queue to know how to label. So do it as you work on assessment queue. Don't finish the question and then come back. So do it as so you label it while you're busy. Otherwise, it's going to take too much time. Just do this quickly. This one. Here we go. So first table I just purely copied from the original optimal table because we're redoing the question basically. You redid the question, just with a different algorithm. So copy that. Make sure I make a space for the new slack due to that less than or equals to, and add my new constraint that I now created. All right. Anika, you good? Cool. So how do you guys feel about getting the optimal solution like so quickly? Okay, but I have to warn you, it doesn't always. And I have warned you that it doesn't always give you the best. Okay, it might give you something very close to the best, which does already give you something to work with. Sometimes you might be cutting and cutting and cutting and cutting, and you're like, oh, I could have just done branch and bound. So yeah, in some cases you smile, in some cases you just know, yeah, maybe not. Right. And an easy cut. Yeah, if you just said cut, I would be like, No, we're gonna ask you to do both in the first test, definitely. Definitely. Maybe in other tests we can specify, and in your assignment you have to do both. But yeah, that's both. All right, so we got the optimal solution because we're done. But guys, please remember dual simplex check. This is a max problem. Once you have no more negatives on the right side, please check if the Z row is also optimal. Max problem, there are no negatives, so yes, it is optimal. If this was a min problem, I would have to pivot because that's the largest positive I have to pivot. Please don't forget that. Okay, it doesn't always work out perfectly that you don't just do one phase. Then also, if you had to cut again, let's say this was a 1.8 at x2, then you're now going to have to go with x2, highlight where x2 has a 1, so I would then highlight this, and let's say this was 1.8. There's no choice. I mean, the other one is an integer. I'm happy. But if this was now a fraction, I would go highlight that where the 1 is for that value, of course. Write it down, repeat the steps, get a new table where I now copy this table and add on, like I showed in that first image where I said with cutting, you literally go and you add on, new cut until all the values that you want integers are actually integers. Okay, same check if you had more than one, same check. Okay, but you're building on the table more and more. Okay. Armandre, you saw now that dual and primal is part of it, so it will definitely be there as well. It's still exactly, yes, Ron. It still falls in this topic, so it will definitely be there. You will still definitely need to get an optimal solution before you can start. So that's where Solver comes in to make sure you don't mess anything up. All right. So I'm going to go quickly recap Solver very quickly for you to help you with that. Okay. Not likely. I can't promise you, though. I can't really tell you, but it's not likely that it will be a question on its own. I have seen before in exams where they might put in a question so that they give you, for example, in branch and bound simplex, they then give you the solved solution, and then in a different question, they ask you dual just to check if you actually knew how to do it. Sometimes, but I can't promise that. Okay. Unicurve cutting plane, we don't know. That's a sad part. We don't know. We're going to use Solver to do the checking, though. I mean, you can use Solver. Then you can show that, okay, well, unfortunately, with cutting this piece away, you cut away the most optimal one. So Solver would be your way to check that the cutting algorithm actually took you to the correct one by cutting, actually. So we're going to include Solver now just to be able to have a check, to see that because all of this is to have the correct tables, and to have an algorithm that you can actually run through and get the answers, actually, right? But yeah, if you can first do branch and bound, that's a very good idea, because then you can actually use it to check your cutting plane. That's a very good idea. So that if you're doing cutting plane, especially for your project, for example, and you see that the Z value is 41.25, and now you cut and it becomes 40, and you know for a fact that you had a candidate that's or the base candidate that is, maybe the value was, I don't know, 35, then at least you know, oh, I'm going down, so it's going there. But if you now all of a sudden get a value of 100, but your values were 41.25 and 40, and now you get 100, now you might ask yourself, what am I doing wrong? It's not supposed to change that drastically. It's still supposed to kind of lead you to closely the same Z, changing small pieces. Do not cut away too big part, if that makes sense. Let me just change that back. Right. So it's definitely best to start with branch and bound simplex to have an idea what you're working towards in a test, of course. Right. Always, yes, please always check if you can. If you worked a bit too slow and there's no time for Solver, I mean, go on, fill in as much as you can. But if you then have some time to just go check, please do. But the part that I'm going to tell you to please check no matter what is your optimal solution before you do branch and bound simplex or cutting plane, because you don't want to start with the wrong solution. If your IP was wrong, yeah, then you cry, because, well, Solver is not going to help you there. Usually the IPs are so easy, like this one. But yeah, make sure you use Solver, please. So let's have a look at Solver very quickly. So I'm just going to copy the IP there. Right, so we've got our IP. I don't know how you guys did it last year, but usually people just tend to shift their headings around, but it's still the exact same thing you do with Solver. Okay, so I'm going to put it my way that I normally do. Put all your variables. No S's, no E's. Solver does that at the back. You're going to have your referencing column. Then you're going to have your sign to show which signs are the constraints, and you're going to have your right-hand side. Then we start, this is our decision variables that we get, so meaning those are answers. Then we're going to start with our objective function. Objective is fine. So the coefficients there for the objective function is 8 and 5. No taking over, nothing. You put it in as is subject to. So we now have our constraints. So it's 1 and 1, 9 and 5. Those are our constraints. Both are less than or equals to. The top one is 6 and the bottom one is 45. These are just sign restrictions, which we'll talk about soon. Okay, so I'm going to not do it too slowly because it's just Solver. So we always start in your objective function. You say equals sum product. Some of you might be like, oh yeah, sum product. Right, sum product. The first array that you have to select is the decision variables, and you have to lock it so that those don't move when you drag your formula down. And so you have to lock it once. I'm just going to pause a second. So for your first array, highlight the decision variables and lock it once. Be careful when you click. All the dollar signs must be there. Okay. Check on Excel for you. Mine requires a semicolon there in between. If yours need a comma, then you use a comma. Right, you'll see the array 1 is bold. So I'm currently working with array 1. So if I press semicolon, it's going to go to array 2. So I know, okay, at least I used the correct symbol. Now at array 2, you select the objective function. No locking, because you want to actually move it down and drag and copy to constraint 1 and constraint 2. Okay. Press enter, copy your formula down. All right. Copy the formula down, click and drag down, click in that corner, drag it down, like we've been doing, copying the formula. Okay, now click in the objective function, or it doesn't really matter, but you'll see. Just make sure you have solver actually in. So you'll see now on purpose I don't have it there. So I'm just going to do this once. So if you don't have solver, you go to file, you go to options, add-ins. Then you're actually going to look for solver add-in. It's usually there in the front. And you click go. Once you click on go, you have to make sure it's ticked. Right, you can use other tool packs for other stuff, but yeah, we only need solver. So make sure it's ticked. And then when you come back, solver will be there. All right. So when I click on solver, you'll see set objective. So it's the reference value, not the actual coefficients we put in. It's the reference value that you have to click on. Okay, if you already clicked on it before, it will automatically be filled in. Choose if it's a min or a max problem. It's a max problem. Okay, I'm happy with that. In the changing variables, those are the values that will change based on the solution. So those are the empty blocks, the decision variables. Those are our answers, the solution, the changing variables, the values that will change based on the solution. Now we have to add constraints. So if you have the same sign, you can do them all at once, but I'll do it one at a time just to show you, just in case you can't remember. So you take the referencing cell, not the values, the referencing cell. Make sure it's less than or equals to, because that's the sign we said. Less than or equals to what? That value. Add. Next one. This one. Less than or equals to that value. That's the only constraints I'm going to say okay. Okay, now, even if you're busy on your own, you focus. Please focus. Even if you're doing something on your own now, you focus. Right, because this will help you. So right now, you have to check that the sign restrictions specify that x1 and x2 should be greater than or equals to 0. That means non-negative. They should not be negative. Okay, so that box must be ticked because you're making anything that's unconstrained, so URS, anything that can be negative, you're making positive. Right. If you wanted the values to allow negatives, like x1 can be a negative amount of tables, then you untick. Then you have to specify if some had to be positive. Right, but in our case, we want everything to be positive, so we make sure it's ticked so that everything is non-negative, meaning positive. Okay. Then we say simplex. Now I'm going to solve without anything additional. So when I solve as is, you will see we get the fractional answers. So now I can already make sure that the optimal solution I started with is correct. The Z is 41.25. The sheet, yes. X1 is equals to 3.75. X2 is equals to 2.25. Did I get those? Yes. So at least I know that optimal table that I have is actually fine. Okay. Now I need your focus again. What do I now do to figure out the best integer solution? Okay, so in this case, this just gives you the normal solution. Now you have to figure out, but okay, what if I wanted to check if my best solution is correct? Right, because you can. Solver does allow you to do that. So you go back to Solver. You're not going to retype anything. You just go back to Solver. Okay. Yes, Henry, perfect. So you're going to add a constraint to do that. Okay. So there's more than one way. You can literally go and add constraints in terms of one int, but it's not going to be, there's going to be no point in doing that because you literally have to just click buttons to say int. I'm going to show you now. So you're going to add a constraint because it is a constraint. You don't want it to be anything other than integers. Okay. Then you go and say the answers or whatever answers I want to be integers. So if you just wanted x2 to be an integer, you just select x2. And then you go specify. I want that to be int. And I hope int, you see the binary for your assignment. But anyway, int, right? Then you add that constraint if you only wanted x2. So if that's the case, I would say, okay, solve. Now only x2 is an integer. Got a solution. For this one, though, we said both of them need to be integers. So I'm not going to just add a constraint for the one. I have to add it for both. Select the answer, say I want an integer, and solve. And there we go. I can check my best solution. Please use this, please. Right. All of this in LPR 381 is about learning the algorithms, but of course, Solver is there to help. So please use it. All right. No, Mandre, that's perfectly fine. You can drag both of them at the same time. That's 100%. To show you. So you can do them both at the same time, like Mandre did. I'm just going to quickly delete those. But if you only wanted one to be an integer, you'll just select that one. Okay, but we wanted both, so you can select them both where you have the answers. So you're basically telling Solver, these answers need to be int. Okay. So you say those answers. So wherever you get your answers, that you specify as a constraint, and you say, make those int. Or if you wanted binary answers, you'll say bin. Okay, cool. Right, and then you solve, then you'll be there. Right, you'll see the sheets that I have uploaded. It does have the sum product up, but the solver part, I mean, click around, you'll probably figure it out if you got a bit stuck there. But I just wanted to give you a quick recap if you felt like, I don't know even where to start, okay. Right, then I have something to give you a tip for your assignment purposes. So for your assignment, we are still covering binary problems later. But I want you to know what to do with branch-bound simplex. We've given you a hint. Right, so right now, if you just look at this IP, we wanted integers. So not a problem. We solved branch-bound simplex, not a problem at all. But if I look at the answers that I got, And I told you this had to be a binary problem. So binary would just mean in terms of not the number of, but are we going to make tables or not? And you'll see the knapsack problem is what we refer to. That's literally putting items in a bag. Either we put it or we don't. That's why it's binary. Okay, so 1 meaning it's actually in the bag, so we put it, and 0 means we leave it. It's not going to be in the bag. So just to give you a heads up there. Now we say, okay, we want it to be binary as well. Great, binary, great. Okay, not difficult. We're still going to teach you how to do other algorithms. But with branching bound simplex, you can still do it. You just need the IP. And one additional step. So this is very key for all of you right now. So the additional step is to say, if I solve this as is, I want you to quickly check our first solution that you now literally had on Solver, for example. So I'm going to just delete that again and solve. Do you think those values are close to being binary? If you just look at those values, what do you think? Are they close to being binary? Like that down, like no, they're very far from it. Okay, so if you had to get those answers first, it's very hard to get to binary from there. So what would help you is to say from the original IP where you had to relax and whatnot, already add constraints to limit it to not go past 1. Because binary can only go to be a 0 or a 1. You don't know what 0, what's going to be 0, and what's going to be 1, and what's going to be 0.5. You don't know that. So you have to just limit it to not go past 1. But anything below that would be fine. So hint, in that case, make sure you add constraints for every single variable to limit it to not go past 1. Wink, wink, right? For every single variable. Guys, if you had 6 variables, you'll have 6 extra constraints to limit it to not go more than 1. And that's all I can say. That's my wink, wink. Can't give you more than that. Don't punish yourself and try to solve and then get to a 2.5 and you're like, but how do I now go to 0 or 1? Add those constraints from the beginning. So that when you do dual simplex or primal simplex, you have those constraints in already bound. And Danilo, I'm not going to confirm yes or no. You got the wink, wink. Basically, what I said is clear. That's all I can say. Last one, but make sure it can be 0, 0.1, 0.2, 1. But add it before you solve anything, right? Don't try and decide how to do that. It's just some advice. Otherwise, assessment queue will be a nightmare. Okay, now you're going to have some time to practice. You have a lot to practice, though. A lot. Tomorrow, we're starting with something new. And let me just see quickly. Just want to close this. So I just want to show you LPR. So we have tomorrow task assignment and then on Thursday capital budgeting. So fully, so it's really up to you to make sure you do the exercises and go check what solutions I have uploaded. Then when we continue with other topics, you'll see in my notes on BC Connect, I said you have to simply if you can. Right? Always, always. Right. But I'm not going to continue talking, especially if there's a lag. Now we have done what we needed to do. We'll continue with task assignment tomorrow and a small bit of the exercises. So make sure you do all the exercise. Assignment is long, so we're going to spend some time on it. So I'll be kicked out again today, but yes, everything will be in the test that we cover. Everything will cover. So that's what's up as well now when I'm done talking.